Right, the 2009 materials and the use and structures section. Again, it starts off with the same graph we're used to seeing over and over again. We've got two, hard steel and soft steel, and they're being tested under tension. Alright, the first one, compared to hard steel, soft steel can be best described as, so soft steel here. Is it stiff? Well, stiffness is the gradient of the graph. The bigger the gradient, the stiffer it is. It's not stiff. Is it strong? Well, no, strong's the stress to the breaking point. Hard steel is the strongest. Is it brittle? Brittle is having a small plastic region. Hard steel has a small plastic region, so it's not brittle. Hard steel is brittle. Soft steel is ductile. It has a large plastic region from here to here. So soft steel is ductile. Which of the following statements indicates that hard steel is stiffer than soft steel? Stiffness is the gradient, or steeper gradient. We'll have that definition somewhere on our cheat sheet. So which one of these says it has a steeper gradient? Hard steel undergoes less plastic deformation than soft steel? No. Greater stress is needed? Diffraction? No. The area under the graph is greater? No. The gradient of the stress strain curve is greater for hard steel than soft steel. There we go. Number 3. Which of the following statements about toughness is correct? Toughness is area under graph till breaking. Which of them has, of those two, has a bigger area under the graph until breaking? Is it hard steel with all this area? Or is it soft steel with all this area? It turns out it's soft steel. If you, that's almost to 16. If you were to grab this section here from, oh, that's to 15 there, so to 30 there, this section here, and plonk it up there, would sort of look like this. So this green stuff has more area than the red one. That's just how I sort of compared them. So soft steel is harder than hard steel. Right. Question 4. Soft steel has an initial length. It's placed under tensile stress. The strain produced by the stress is this strain, epsilon. What are the options for the best estimate of the length under this rod under this stress? So we've got the formula epsilon equals change in length over initial length. So we can rearrange it to find change in length equals epsilon times initial length. So we'll just put those numbers in. 1 by 10 to the minus 3 by 10. That equals 0.01 meters. So that's the change in length. So if we started off at 10 meters and it changed by 0.01 meters, it's under tensile stress. So did that get smaller or did that got bigger? If you're putting something on tensile and stretch, it would have been stretched. So that's going to be added to it. So the new length we get is 10.01, which is D. Which of the following is the best estimate of Young's modulus for hard steel under tension? Right, this is Young's modulus is rise over run, or stress over strain. I'm just going to pick any points on here for hard steel. In this straight line section. So what I'm going to do is I'm going to pick this point right here. which is at 400, and which is halfway between these two here. So it's at, that's 4, so it's at 2.5 by 10 to the minus 3, and it's at 400 by megapascals. A mega, or they've got it here, is at 10 to the power of 6. So that was my 400 by 10 to the power of 6 over a 2.5 by 10 to the minus 3. You do that calculation, you get 16,000. No, my mistake. You don't get that. You don't get that at all. You get 1.6 by 10 to the 11, which is D. Alright, same graph again, and question 6 and 7. Cylindrical rod of length 2 meters and cross-sectional area cut that off, did I? Well, I think it's by 10 to the minus 5. It's made of hard steel. The rod is placed under tensile stress, 200 megapascals. That's your area. Which of the following is best estimate of the force that must be applied to provide this stress? We've got stress equals force over area, so we've got force equals stress times area. Here's our stress, 200 megapascals. A mega is a 10 to the 6 by the area, 8 by 10 to the minus 5. And that is the one that I had wrong, was 16,000 newtons, which is 1.6 by 10 to the power of 4. And last one. A stress of this is applied to a 100 hard cylindrical rod which produces a strain of this. The strain energy per unit volume is closest to. Now, this is something you have in your cheat sheet. This is always the hardest one of these questions. This is the area under the graph. Under graph. And it's at 200 megapascals and at 1.2 by 10 to the minus 3. Where is that? Well, that is actually right there, and goes down to there. It's just that little tiny bit under there. So there's not much area at all to work out. It's going to be quite hard to count the squares under there. But what shape is that? Well, this goes straight up, and then the shape under there is going to be a triangle. So it goes up to 200, and it goes across to 1.25 is what they gave, I think. Yeah. So I'm just going to do it, it's a triangle. That equals half base height. Half times the base, which is this one here, 1.25 by 10 to the minus 3. Here's your 1.25 by 10 to the minus 3. And the height is 200 megapascals. Yeah, there it is there, 200 megapascals. 200 by 10 to the 6. And when you calculate that, you get 125,000, which equals 1.25 by 10 to the 5, which is the closest answer, 1.3 by 10 to the 5. There we go.